In the realm of scientific discovery, there is a quest that has captivated the minds of physicists and engineers for decades. It's a quest for a material that could revolutionize the world as we know it, a material that could unlock the secrets of the universe and usher in a new era of technological innovation. This is the quest for the room temperature superconductor, the holy grail of physics. Imagine a world where electricity flows without resistance, where power lines and electronic devices operate with perfect efficiency, and where the limits of human innovation are boundless. This is the promise of superconductivity, a phenomenon that has fascinated scientists since its discovery over a century ago. Superconductivity is a state of matter in which a material conducts electricity with zero resistance. When a material becomes a superconductor, electrons flow through it without any energy loss, creating a current that can persist indefinitely without the need for a power source. It's a phenomenon that defies our everyday experience and challenges our understanding of the physical world. The discovery of superconductivity dates back to 1911, when Dutch physicist Heike Kamerlingh stumbled upon the phenomenon while studying the properties of mercury at extremely low temperatures. Hans found that when mercury was cooled to just a few degrees above absolute zero, its electrical resistance suddenly dropped to zero, indicating the presence of a superconducting state. Since then, scientists have discovered many other materials that exhibit superconductivity, from simple elements like lead and tin to complex ceramics and even organic compounds. But there's a catch. All of these materials only become superconductors at extremely low temperatures, typically below -140 Celsius or -220 Fahrenheit. This temperature limitation has been a major obstacle to the practical application of superconductivity. While superconductors have found use in specialized applications like MRI machines and particle accelerators, their widespread adoption has been hindered by the need for expensive and bulky cooling systems. But what if we could create a material that becomes a superconductor at room temperature? This is the tantalizing possibility that has driven the search for the room temperature superconductor, a material that could conduct electricity with zero resistance at temperatures above 0 Celsius or 32 Fahrenheit. The implications of such a discovery would be nothing short of revolutionary. Room temperature superconductors could enable the creation of ultra-efficient power grids, where electricity is transmitted over long distances without any energy loss. They could also lead to the development of levitating trains, quantum computers, and other technologies that are currently limited by the need for cryogenic cooling. But the quest for the room temperature superconductor has been a long and challenging one. For decades, scientists have searched for materials that exhibit superconductivity at higher and higher temperatures, but progress has been slow and incremental. One of the most promising avenues of research has been the study of copper oxide compounds, or cuprates. In 1986, physicists Georg Bednorz and Alex Müller discovered that a ceramic material made from lanthanum, barium, copper, and oxygen became a superconductor at a temperature of 35 Kelvin, which is -238 Celsius or -396 Fahrenheit, a record high at the time. This discovery set off a flurry of research into cuprates and other high-temperature superconductors, with scientists around the world racing to find materials that could operate at even higher temperatures. In the years since, researchers have discovered many other high-temperature superconductors, including compounds made from yttrium, bismuth, and mercury. These materials have pushed the boundaries of superconductivity to ever higher temperatures, with some compounds exhibiting superconductivity at temperatures as high as 138 Kelvin, which is -135 Celsius or -211 Fahrenheit. But despite these advances, the room temperature superconductor has remained elusive. The highest temperature at which superconductivity has been observed is still far below the freezing point of water and there is no clear path to creating a material that can operate at room temperature. One of the major challenges in the search for the room temperature superconductor is the complexity of the materials involved. High-temperature superconductors are typically made from complex ceramics with intricate crystal structures, and the mechanisms that give rise to their superconducting properties are still not fully understood. Another challenge is the need for materials that can withstand the stresses and strains of everyday use. Superconductors are often brittle and prone to cracking, making them difficult to incorporate into practical devices. Researchers are working to develop new materials that are both superconducting and mechanically robust, but progress has been slow. Despite these challenges, the quest for the room temperature superconductor remains one of the most exciting and important areas of research in physics today. The potential benefits of such a discovery are simply too great to ignore, and scientists around the world are working tirelessly to unlock the secrets of high-temperature superconductivity. One promising avenue of research is the study of unconventional superconductors, materials that exhibit superconductivity through mechanisms that are different from those of conventional superconductors. These materials include heavy, fermion compounds, organic superconductors, and iron-based superconductors, among others. Another area of focus is the use of advanced computational methods to predict and design new superconducting materials. By using powerful computer simulations and machine learning algorithms, researchers can explore vast libraries of potential materials and identify those that are most likely to exhibit superconductivity at high temperatures. But perhaps the most exciting development in recent years has been the discovery of superconductivity in a class of materials known as nickelates. In 2019, a team of researchers led by Harold Huang at Stanford University reported the discovery of superconductivity in a compound made from lanthanum, nickel, and oxygen at a temperature of 9 Kelvin, which is minus 264 Celsius or minus 443 Fahrenheit. While this temperature is still far below room temperature, the discovery of superconductivity in nickelates was a major breakthrough, as it demonstrated that superconductivity can occur in a wider range of materials than previously thought. The discovery also raised hopes that nickelates could provide a new platform for the development of high-temperature superconductors, and researchers around the world are now racing to study these materials in greater detail. As we continue to push the boundaries of superconductivity research, it's clear that the quest for the room temperature superconductor is far from over. But with each new discovery and each new breakthrough, we move closer to unlocking the secrets of this extraordinary phenomenon and realizing the incredible potential of superconductivity. In the words of the great physicist Richard Feynman, there's plenty of room at the bottom. This statement, made in reference to the vast potential of nanoscale science and engineering, could just as easily apply to the search for the room temperature superconductor. There is still so much we don't know about the fundamental nature of matter and the incredible properties that emerge at the smallest scales. But one thing is certain, the discovery of the room temperature superconductor would be a watershed moment in the history of science. A triumph of human ingenuity and perseverance that would transform the world as we know it. It would open up new frontiers of technological innovation, from ultra-efficient transportation and communication systems to quantum computing and beyond. As we stand on the brink of this incredible possibility, we can only marvel at the extraordinary complexity and beauty of the universe we inhabit. We are reminded that the quest for knowledge is a never-ending journey, a constant push to expand the boundaries of what is possible and to unlock the secrets of the cosmos. And so the search for the room temperature superconductor continues, driven by the passion and dedication of scientists and engineers around the world. It is a quest that will require patience, perseverance, and an unwavering commitment to the pursuit of knowledge. But it is a quest that holds the promise of a brighter, more sustainable future for all of humanity.